Oh, wait, no, that's not actually the talk you're going to be giving. No, I'm actually here running streaming, very much looking forward to this talk on building genuinely trusted computing that you can actually audit. So please, everybody give a huge round of applause for Ryan Lackey.
Okay. Good morning, everyone. So today we're going to cover why do you need to trust your hardware, some historical and current solutions in the space, design goals and some building blocks to build something better, an open design, and we're going to have a discussion about how this should proceed. Just as a brief intro who I am, I guess I got involved in cryptography as a cypherpunk back in the 1990s, like 92, 93, when I was like 12 or 13 years old, and I was really interested in eCash. And back then, you couldn't export crypto from the US, so I moved to this little island, Anguilla, to work on some open source anonymous electronic cash. Learned a lot about cryptography in the process, and also about living outside of the US and working on cool stuff. Then started an offshore data haven, HavenCo, back in 2000. It was a World War II anti-aircraft pirate radio platform that declared itself a sovereign country back in the 60s. We set up a bunch of data center stuff on it and did a bunch of hosting. It was like a really big thing for about like 2 or 3 months, and then sort of like a less big thing for another couple of years, and then sort of like there was a fire and some other stuff. Then I worked on RFID and NFC payments, so cool stuff where you use tamper-resistant smart cards and things to do NFC payments. If you go to a Jack in the Box, you'll see some stuff that I worked on. I actually went to Iraq and Afghanistan from 2004 to 2010. I worked on satellite networking, cellular systems, wireless communications. I bootstrapped a small defense contractor with like $2,000 and lived out in the wilds of the city and didn't get killed, so it was pretty fun. And now I have a trusted computing startup, CryptoSeal. Since 2011, we've been working on some cool stuff using some of this technology, some other technology. We have some cool stuff to announce, but that's going to get announced later time. So the big question is, why do you care about this at all? It's because there's some threats that you face as a computing user. You face these as a sysadmin, you face these as an end user of the system. These are physical attacks on your hardware. If anyone gets access to your physical hardware, which normally your employees do, they can do all sorts of crazy attacks. They can image the contents of your disk. They can add hardware to it in the form of implants to do key logging, to do all sorts of other crazy stuff. They can tear it down. They can put it in a scanning, tunneling microscope. They can use a focused ion beam workstation. They can pull keys off of it, all sorts of crazy stuff. It's not so scary when it's a $5 million lab required to do this, but some people, Zach Brown and Adam Laurie, have actually gotten it down to like $10,000 or $20,000 worth of hardware to do some really aggressive attacks using like common off-the-shelf things from eBay. So it's kind of terrifying. There's all sorts of attacks, obviously, if you get system console access to a system. You can usually bypass most system access control mechanisms. Static crypto usually does protect you, but doesn't protect you from the evil maid attack. And my friend Eric Michaud and I have been working on some systems to detect evil maid attacks using nail polish, auto paint, and an iPhone as like applied to surfaces, which is kind of cool. Of course, if you get access to a system locally on the system, if you can do a root exploit, you can run all sorts of memory attacks. You can read out any location. You can do stuff. And there's also the blue pill attacks, hypervisor attacks, everything else. So it's pretty scary. And of course, in the cloud, you don't even see your hardware. You might never see your hardware. So you want a property called remote attestation where you can prove what's running on a remote server. And you don't even know if you're talking, if you're dealing with a virtualized environment remotely. So it's a pretty scary thing. But there's one really big threat that all of this stuff, insiders. We've seen organizations that have $50 billion year budgets with huge amounts of screening for employees and physical security, software security, best-in-class cryptography, everything else fall to a single insider. So if you think they have great mechanisms to protect and they still fall against it, if you look at your organization, you're going to have even more problems. So generally, people are worried about protecting a few kinds of things. At highest level, they're trying to protect keys, so they can do access control on those keys. They're worried about the general data you're processing, and they're worried about integrity and provenance of calculations. So you want to make sure that the keys you use in cryptography are protected, because these are usually long-lived keys. You can have keys, like I stupidly have a PGP key from 1999 still. So the compromise of a key during any of that period can be a major problem. Data confidentiality is usually protected less than the keys, but Still, it's a big problem if you've got, yeah, so, yeah. But this is a really, really hard problem to solve. It's gotten harder recently, or at least we know that it's harder recently. You don't really know when you look at your off-the-shelf computer where every single piece of that device is made. Anything that has DMA access to your memory, your video card. So basically like your video card, the ADC dongle that I have plugged into my laptop that has DMA access to my computer as it does the video output. Anything else can be doing anything in main memory it wants to do. There's some ways to mitigate that, but they're not foolproof, and there's always new threats. You have to audit every piece of software, every piece of firmware, everything else. And yeah, it's difficult. And the systems that people build to resist this kind of thing give up a lot of really important properties. They're designed, generally they're not as open, it's hard to write software for them. It takes much longer to write software for them. If you look at the schedule for a secure payment system, like the smart card-based payment systems, those guys spend like 5-6 years doing something that in software you could do in a couple weeks to get deployed in the field. So yeah, big problem. So there's a lot of cool technologies we're going to go over, but they do have some drawbacks. One of the big things that I've discussed with Seth Schoen from EFF since, I think, 1998 onwards is the risk that, like, this is a powerful technology, but it brings a lot of risk. If you build it and it gets used widely, there's a potential for effective DRM. So I don't know, I assume everyone's heard the Richard Stallman Right to Read paper where some arbitrary date in the future you can't tell, or you can't share books with people, you can't do anything like that. It's definitely a possibility. Luckily to date, DRM technologies have been pretty half-assed, so you can mostly bypass them, but there's a potential if you build a really strong DRM system that you won't be able to bypass it. And the other thing is you might have to be a licensed software developer to write software for something, and once it's possible to do that kind of thing, then some regulatory agency might decide that you need to have a special certificate. Certainly vendors right now, like if you look at the mobile development environment versus the PC environment, they definitely have developer programs. You have to pay a certain amount of money or whatever else to start developing for their platform. And that's really, if you look at all the cool stuff that's happened in the last 20 years, it's usually happened by people that are hacking on stuff without permission from the hardware vendors. And there's a threat that Joanna Rakowska has proposed of basically malware which can't be reverse engineered. So if you build a really strong system that protects you from people inspecting things, you might end up with a system where you can't tell what's going on in your own system, and that's a really terrifying situation. If you've seen CryptoLocker and the horrible stuff that CryptoLocker has been doing and how successful it's been, imagine something far worse than that. And there's all the people that worry about what happens if strong cryptography, strong hardware security, and everything else exists, like assassination politics and all this other stuff. I think there's enough steps in that chain that I'm not too worried about that particular threat. So back in the day, people had a pretty decent solution to this problem. It was to basically own every single piece of the chain. They would design their own hardware, they'd fabricate it themselves, they would assemble everything, they put it in their own data centers, they'd have their own staff that are vetted and secured, everything else, and trust every operator. Obviously, we've seen the problem when trust every operator is required, and we've seen over the last like 60 years of computing the problem with hoping that there's no bugs in your hardware or software that are security relevant. So it's also hugely capital intensive. It's pretty feasible if you're going to do something very small, but if you're trying to do a really big project or anything that's like actually useful in the field, you can't really own the entire chain from like making from sand all the way to your final product. One solution that people have had is the thing called a hardware security module. There's some commercial vendors of these, Encipher, which is bought by a French company now, SafeNet, which is a big US company, and there's a few more. There's IBM, who makes the 4758, 6465s, Ultimaco, there's a few more. The problem is these things are really expensive. I buy them off of eBay for like $300 each sometimes, but I have pretty low odds of them actually working, but they're like 20, 30 grand each. You have to be a part of their developer program. You have to get a license to write code for them, all sorts of craziness. And they're like the opposite of open. And the problem is, fundamentally, they're a huge bottleneck. Aside from not being able to get access to them, they're like the ultimate black box. You can't look inside them without destroying them, and you don't really know why you can trust them. Like somebody at the Real World Crypto Conference actually held up FIPS, actually a guy from a disk drive company, held up FIPS 142 certification as like a good reason to trust something, and yeah, though maybe not. And the other problem is if you're trying to use these in the cloud, they're these devices that are like PCIe cards, or they're rack mount servers, or some of them are like old SCSI devices and things. Trying to get your cloud provider to be willing to use them is kind of tricky. I know Amazon does something called Certificate SIM using the SafeNet product, which has some serious drawbacks as well. It's also super expensive. But most cloud providers, if you try to tell them, like, I'd like to plug something into my cloud server, it'll be pretty crazy. So these things exist. There's also smart cards, which you're all familiar with from GSM. Is probably the most successful thing, at least in the US. And there's a lot of cool payment systems that have used them for like 20, 30 years. Octopus in Hong Kong is probably the biggest one that I've seen. They're usually used for like mass transit stored value cards. They're pretty cool. They're really slow. I guess you can get 32-bit ones now, but they used to be like 8-bit until relatively recently. And the big problem is they don't actually have their own power source, so they only work when they're plugged into something. And the problem with relying on an external unfiltered power source for your operation is that exposes you to a lot of attacks, and it prevents you from doing a lot of interesting counter-tamper technology. So they're definitely a solution. There's also some stuff that's in between. There's Yubico, which is a Swedish company that also has offices in the US that makes something. They make the cool little like YubiKey. It's like a both one-time password type system. They make a thing called a Yubi HSM, which is a $500 thing, which is sort of similar to the rest of their hardware, and is used just for their own authentication system. It doesn't do any public key crypto. It doesn't let you run arbitrary code. And it's really cool for their particular system, but it's not really useful in general. But it's a sign of like something that we could build. Another solution is there's an organization called the Trusting Computing Group. So a minor history lesson or horrible reminiscing. Back in the late 1990s, there was an effort by Intel, Microsoft, and a couple other companies, mostly media companies, to build something called Palladium. It was a big DRM system that was designed to allow media companies to not worry so much about people stealing DVDs and MP3s, or I guess CDs back then from their computer. It was horribly rejected by the market. Like, I was horribly against it because of the problems of having to be licensed to write code and everything else. It also technically was really, really complicated and generally unsuccessful, but it was so hated by the market that like this whole field got vilified for a few years. And the only reason I started working on this stuff again back in like '06 was I talked to Seth over at EFF, and we sort of weighed the compromises of having this technology versus the compromise of not having the technology, which is everyone getting owned all the time by everybody. So this huge like DRM backlash has been a pretty big problem. This is the thing that uses the TPM on your motherboard. BitLocker from Microsoft in Windows 8 is probably the most widely deployed system that uses this stuff. Intel TXT is like the server version of vPro. It's basically a server technology that lets you do some cooperation with your hypervisor or with the operating system to do remote attestation and some other stuff. AMD has an equivalent product, SVM. There's a sort of related technology from ARM called TrustZone, which is actually in many ways better, is definitely simpler, but you could put it all in the same category. There's this new really amazing thing called Software Guard Extensions, or SGX, from Intel. They announced it, I think, in the summer at a developer conference with really no fanfare. It's been really hard to get documentation about it. They released a great white paper back in September and some other stuff. It's pretty much like the Holy Grail. Unfortunately, it could be. We don't know for sure exactly what it will do in a couple of areas, but it looks pretty awesome. But the real problem is we have no idea when it's going to ship. It's not on any roadmap. I've heard it'll be in the next generation after the next generation of Xeons, but with a pretty low confidence figure. It'd be really awesome. Basically, it lets you set a secure enclave on your CPU that can be protected from the hypervisor, from your operating system and everything else, operate, and if they build in a PKI so that you can tell that it's a guaranteed Intel processor, you effectively get all the benefits of this trusted computing technology and only have to trust Intel. Like 3 or 4 years ago, I would have said that would be perfect because, I mean, Intel, this big company, big amazing company, great hardware, great designs, trustworthy, especially building a mass market product. They're not going to want to backdoor it, but maybe the last year people are less willing to just blindly trust a large vendor like that. So it's definitely a technology to watch. It's very, very interesting. I'm looking at it as much as I can, but it's probably not the usable solution for the reasonable time period. There's some cool technologies that are out there that all use virtualization. So virtualization definitely brings some security problems, but I think it brings more benefits than problems, even in security. It's definitely a usability and cost savings and everything else advantage. VMware actually ties into Intel TXT in some fairly lightweight ways, just to prove that you're talking to a real VMware server, as long as you trust Intel and your TPM vendors and everyone else. It does some cool stuff. There's a company, HighTrust, that does basically like encrypted VMs. The cool project is actually Tresor or Trevisor, which are from a European academic researcher or research group. Essentially, on your CPU, you've got this huge L1 cache, or decent-sized L1 cache, huge L2 cache, and incredibly huge L3 cache. So, and you've also got crypto operations that are hard-coded into your CPU. So one of the awesome things you can do is actually pin one of your CPUs to, or at least a core, to keep code for all this encryption routine and a hypervisor inside the cache itself, and use the CPU hardware to do all these calculations and operate. So effectively, everything that leaves the CPU is encrypted and signed, and it has integrity protection. So you can do really awesome stuff there. The CPU is like the latest generation of process technology, so reverse engineering a late model Intel CPU is actually beyond the $20,000 or $30,000 lab scale. It certainly can be done, but it's on a live system, but it's not something that I know anyone who knows how to do. I think even the guys that I know that know how to do this stuff can't do it very easily. So there's that. And there's actually a company called Private Core that's been at RSA and a bunch of other conferences and presented stuff and has a cool technology. It's basically like Trevisor, but a little bit better with all the stuff sort of working. It's not a public system yet, but it's a pretty cool thing. So there's that. Another solution, of course, is secure multi-party cryptography. So you can basically have a bunch of components that you don't trust fully and have them work together and know that as long as you trust at least one of those components, you're not screwed. So this works exceptionally well for very specific cases, like public key sharing with multiple devices. We have some great algorithms that do that. Unfortunately, the general systems require creating a circuit design and evaluating and all sorts of other stuff, and they're really, really slow to execute, like infeasibly slow to execute. There have been some recent breakthroughs, actually, at Real World Crypto. There's a cool result that a lot of existing algorithms are highly amenable to this kind of calculation, where you use like SHA-2, where you can do a small part of the calculation in a trusted device and then a large part of the computation in an untrusted device. Cool stuff like that. But I definitely put this more in the like theoretical math range and not in a useful system for now. So today there's a few options. The guys that do DNS and hand out your IP addresses, or I guess now they don't hand out your IP addresses anymore, have this cool project. It's part of DNSSEC because DNSSEC requires a device. It's basically a very, very small, cheap device that's maybe like 3 inches, 3-inch PCB board, very cheap, like I think it was like $50 target price. And it can do arbitrary calculations. So the big difference between a lot of these things is they're designed just to do key management, and they can only do, you can have your host computer talk to them and ask them to do a calculation. You can say like sign this string or decrypt this item. Unfortunately, that's not really sufficient for a lot of use. The problem is if you've got a device that whenever you send it a message, it signs it automatically. Somebody just has to walk up, take the device, put it in their own thing, and start getting it to sign bogus stuff for them. You really want to be able to run application-specific code inside your HSM to validate requests rather than run it as sort of like a blind trust anyone thing. This is really, really cool. He started on it, I think, mostly 2011. There have been a couple papers about it. They've definitely been advancing the design. I don't think they're really in the hardware business or anything, but it's a great design. A lot of people have come up with a fairly obvious solution, which is to take some sort of small single-board computer and put it in a nice tamper-resistant case. I think I've seen like 6 different projects in this space. There's a few problems with using Raspberry Pi, which is like the most appealing thing. TrustZone, which is one of the most useful technologies for this kind of thing, doesn't exist, at least as far as I can tell in that. And the problem of making a physical enclosure that's physically tamper evident is difficult. Making one that's physically tamper responding is definitely difficult. And the whole problem with this whole space is it sort of falls into like the intersection of a few fields. You need to have some level of cryptographic knowledge, some level of like building computer systems, general systems engineering knowledge, and some like weird hardware knowledge. Like this isn't, it's sort of opposed. Like the ways you build hardware to be reliable and easy to mass produce are exactly the opposite of the ways you build hardware to be tamper evident and tamper detecting. So it's very difficult to find people who have all these things. So most of the hobbyists that have been working on this thing have had some problems. It's pretty fast though. Like a Raspberry Pi is actually a pretty decent computer, so there's that option. There's also the thing called the crypto stick from GPF, which is essentially a smart card. There's no smart card, it's just a security processor. It's mostly used for key management. I've seen PGP, OpenPGP used on it, some other things, but they're pretty limited in functionality. It's a project in Germany, basically another smart card HSM type project. Kind of cool. I have never actually seen this, I just researched this a little bit. So the conventional solution, if you're kind of going to try to do a one-time calculation or an infrequent calculation, like signing your keys for your server, if you're not willing to spend the $30,000 on an HSM, is to go to like Costco and buy a random laptop off the shelf for cash that's randomly selected, hope it's not bugged, and hope your software that you install on it's great. This is great for infrequent operations, but you have to build, because the problem is your number one threat is insiders, and anyone who has access to the laptop can put all sorts of crazy software or hardware modifications into it. So you have to build a lot of procedure and ceremony around how you handle that laptop, like making sure that the people who can modify the code never actually touch the laptop, all sorts of other stuff. And it's really, you can probably do this viably within your organization, but proving this to other people is very expensive. Like I have no particular reason to trust that anyone is going to do this consistently if they say they are. And it really only works in an offline model. If you leave it online to the internet, you're going to expose it to all the normal vulnerabilities. It works in an air-gapped type system. And what people normally do is they just have like a single task lockdown server. Traditionally, like if you've got like a logging server or something, there's no reason that there should be no reason to read from that device on the network. So just people used to take serial cables and cut the one side of the pairs, do things like that. Data diodes, one-way things. It's pretty good. It still doesn't really help insider risk. The guy who can update the software on that server, which you have to do if it's an online server, can do all sorts of bad stuff. So the thing we really want here is we want a limited host to module interface. We want to build a small module that has a very, very small channel and a very well-defined channel between it and the host. We want it to be able to run arbitrary code. I don't want to just have something that's like a smart card that can sign anything and will sign only when requested. I want it to have real logic in there. So it can either do a multi-party authentication thing where I have to have multi-people within the organization sign off on something. But really, I'd like to put my real application logic in it. So if you know that there's no reason, like for like Bitcoin, that you shouldn't be paying out a certain money amount per day or whatever, put that hard code into the device and make sure that it can't do anything. And I want to make sure that the system is designed to be as auditable as possible with very small bootloader and firmware. The secure bootstrap is hard. People in the past have built like crazy smart card operating systems that are multi-application and everything else, but I think that's very difficult to do practically, especially on a limited budget and limited resources, so I want to dedicate these devices to single tasks. I mean, you might end up with a crazy situation where you've got a computer with like a bunch of USB dongles on different applications attached to it, but whatever. And I really want end users to be able to know that they're talking to a real device over the internet. They shouldn't have to necessarily trust the organization to run the system as long as they can trust that the device was built in a certain way. And my focus is primarily on servers. A lot of this DRM, so a lot of the dangers of DRM are actually client device dangers, that you're not able to modify hardware that you own personally to do things like time shift recordings or whatever else. I think servers, there's much less risk of losing people's rights with those servers. I want it to be able to work in a remote or a cloud environment, and the server kind of has two meanings. There's servers that are remote from you, and there's a server process that runs on local hardware to you that you communicate with. The problem is if you want to build a desktop application and you want it to be secure, you have to trust everything that's involved from getting user input to this device and back out to the user. So you have to trust your video card, your video drivers, the screen itself, the cable, all sorts of stuff, the keyboard controller. There's a whole TCP path that is very difficult to build. So I think it's much safer and much easier to build a secure hardened thing that fits inside a server, and then handle the problem of building a secure client device separately. Maybe have multiple client devices, maybe have diverse client devices that can't all be compromised in the same way, or use like a 10-year-old client device or something else like that. And this is all about having very well-defined and limited interfaces. The HSMs have some systems where they're network attached. There's some systems where they can do DMA to the host and things on outside of their security envelope, all sorts of stuff. A lot of those are done for performance reasons or cost savings reasons, which really do matter on a $30,000 device, but they don't really matter so much in like a $100 device. And I want it to be designed for open source applications or free applications or for people that are doing internet services. Right now, if you're building a banking application, you're actually legally required to use HSMs for certain things, so they're going to keep going to the HSM vendors and buying from them. This is for people that aren't using any of this technology right now. And I'm willing to sacrifice performance, especially if it's something where I can just buy more of them when I need more performance. There's actually a standard, the FIPS 140 standard, that does certification of cryptographic modules, hardware, software, everything else. It's a difficult, expensive, slow process. And I'm not really that interested in going through that process because, at least not initially, because it's it slows down development. And the people who require certification are going to stay, they don't care about money, so they'll keep buying $30,000 products all day. And I'm definitely willing to give up the DMA thing. And I'm not actually that interested in making this a you can trust all of these devices solution. I would like to make it more decentralized. So anyone who actually assembles them to an open design is able to become the local root of trust. So if you're an organization, you can have your IT security department build these, do keyload, and they're the only thing that needs to be trusted. And the real problem is that HSMs, because they're this ultimate black box that you can't tamper with without destroying them, are like the perfect backdoor. So the way people have solved this in the past is they just trust their vendor. Big vendor, yeah, sure, you could probably trust them in most cases, but in a world where your packages can be surreptitiously replaced with like a slightly modified product, I would be very, very afraid if I were at all suspicious to purchase a product that I can't verify from a vendor that only sells a limited number of these things, primarily to large organizations that are interested in hacking other people and trusting that they're going to be good. So you can do this thing called cut and choose, where you buy them and you just do destructive teardown of multiple devices. So you buy like 10 of them and you take 9 of them and you shred them apart. But I'm not really in the business of buying like 9 times $30,000 devices and shredding them every single time I buy a piece of hardware. And I don't know how to verify a complex device. It's very difficult. If all you're worried about is having a key leaked, it's really, and you're willing to, or your attacker's willing to come and seize your device afterwards and then try to extract the key, there's so many places you can hide a key in a device. I think this might be like, it's not like MP hard, but like it's a pretty hard problem, and I think it's hopeless. So proposal is to do an open design that uses off-the-shelf commodity components. That's USB connected, and it's an external device, relatively inexpensive, in the under $500, ideally $50 to $100 range. And they're assembled by end users or by end user proxies like your local security department that loads keys. Reusable components, so the idea is that you can actually verify the thing in the field without completely destroying it, so there's a way to reload it. You'll of course lose your certification chain, but you'll be able to recertify it if you're the manufacturer. And I want there to be no like black box component inside that you have to trust. Like on a cell phone, you can build this really nice secure operating system. You can secure Android, iOS, fairly secure, everything else, but baseband processor, black box, DMA access, game over. So I don't want something like that in the HSM, given that this is a target. And I'd like the assembler to have some freedom to customize this. I don't think there's any reason to have one standard design that is the only solution to this. People are going to have different needs, different performance needs, everything else. There's actually some interesting open questions about this whole thing. I've talked with some people from the Tor project about whether an FPGA would actually be easier to verify and harder to backdoor. The advantage, so the problem with single-purpose devices, which like a security processor usually is that a backdoor, you can design a backdoor knowing exactly what the thing does in normal operation. Trying to backdoor a general-purpose CPU that might run arbitrary code that isn't even written yet is a much harder problem in doing that persistently. So if you've got an environment where your hardware might actually be different than like anywhere else, if you just randomize some parameters, it's a lot harder to build a backdoor process. Then only the bootload process becomes a challenge. And Better verification systems. I've actually been working with Eric on some cool hardware verification technology, so you can at least tell that your instance of the hardware corresponds to the intended design of the hardware. The biggest fear is not so much that somebody's going to make like 100,000 devices that are all backdoored with people that are willing to analyze them, but that someone's going to backdoor your specific subset of devices, and being able to match up your device to the reference design goes a long way there. And there's a real big question about Intel SGX and the ARM trust zone and how you could use that in this environment. I mean, obviously something that doesn't require any hardware is far better because it's effectively free. The stuff's going to be built into your CPU. But there's the question of who doesn't trust Intel, there's the question of everything else. So there's all that. And there's huge amounts of work in this. There's the HSM designs themselves, but you've also got to build a tool chain that is able to handle remote attestation. So you want to publish the source code of your application and have the end user verify that that application is what is actually running on the HSM when they're interacting with it, every single time they interact with it. Building something where somebody can get source code and download it and then hash it themselves is relatively straightforward, but the problem of making that part of the like SSL handshake or something else is an open problem. And you definitely need to be able to modify how you build applications. You're not going to put your entire application inside this because then you have to audit your entire application. People need to be able to split their application into something that is security critical and something that's not security critical, run the non-security critical stuff on commodity front-end servers that are untrusted, and only put the security critical stuff inside it. It's a little bit different than the current model where you might use a hardware key protection device, but you want more logic than just the keys inside the device, but you can't put everything inside the device. And the whole problem of secure clients, like I don't know what people use as secure clients these days. There's nothing really that is auditable enough to be great. So in the future, I think the most interesting thing, the thing I'm working on right now, is actually building a VPN server and Tor server. So my company has a VPN service that we ran, and after the LavaBit situation where the keys were compelled under a very, very limited legal resource, the pen register, we shut it down because the risk of that happening to anyone is so pervasive that there's really no defense against it. The bar for getting a pen register order is so low that that everyone has to face that threat. So the idea is that we build a VPN server that you can't actually extract keys from once they're loaded, and any attempt to change it after the fact changes the key, which is visible to the end user. So we can fully comply with the law and give people these keys if they want them, but the user will know the keys have changed, and they'll know to question whether they trust it. And an open source reference hardware design, which I've been working on. It's very difficult to do all in once, so it's sort of an iterative design process. And shoot, I'm talking to some hardware people, and we've got, hopefully by the end of the year, we're going to have something that'll be pretty usable and that meets all these requirements. It's a USB dongle, decent performance, security processor, and then a general purpose CPU inside it. Relatively tamper resistant, basically designed to meet FIPS 143, but not certified. And it'd be really cool to do a DNSSEC deployment with this. And of course, I'm waiting on Intel SGX. If Intel SGX happens sooner rather than later, there's a lot of awesome stuff you can do, maybe using the hardware device and SGX together, or just SGX, so there's that. I'd really like to thank Intel, Microsoft, and the DRM guys for sort of creating a lot of this underlying technology, even with ill intent. Seth and the Tor project, Eric and the Gruck, and I've talked to a lot of people at HSM manufacturers. I think there's actually a lot of demand from HSM manufacturers, CAs, other people that use these devices. They would use more of them if they were cheaper and if they were more flexible. I've used the Encipher products and the IBM products myself. They're really not terribly flexible for developers. They're expensive, everything else. So there's that. And there's actually an upcoming conference, TrustyCon in San Francisco, that's going to maybe touch on some of these issues of when you can trust things. And of course, I'd like to thank everyone for making the demand for this thing a reality. So yeah, I'm going to set up a mailing list and probably get reference designs out to people pretty soon. So if anyone's interested, please contact me and I'll set all this stuff up. So I'd definitely be interested in input or questions or tips or design advice or applications or anything from anyone at this point. I'll repeat, yeah, sure.
Okay, great. Just want to double check that. And then my real question is, how auditable do you think Intel SGX is going to be when
Check.
Yeah. Right. Yeah, so the question is, how auditable will Intel SGX be once it's finally available? So the most interesting thing I've seen recently was actually Seagate's presentation at Real World Crypto, where they built the whole self-encrypting disk drive in a way that's inherently non-verifiable. So I think there might be pressure to make something non-verifiable. I think it's going to be difficult to verify regardless, because it's going to be a complicated device in a top-end CPU that's the latest process and everything else. The design might be verifiable, but we've seen some crazy attacks on, even if you trust the mask of your CPU, just changing the doping at production time can actually change the functionality to completely subvert something like an RNG. So I don't really know. I wouldn't trust it with my root keys for a CA or something. I would probably trust it for a normal server. Like the dream is to be able to run like a cloud service, like a Amazon EC2, somewhere else using this stuff to run your virtual machine and trust it there. I'd trust it for moderate level of security. Certainly better than anything we have now, but yeah, they'd have to have, it also depends on who you are. If you're Intel, you probably trust it because you can keep your supply chain and everything else. If I were a large, closely allied to US customer with the right fabs and everything, I would definitely trust it, or more than I would otherwise. Somebody like WikiLeaks getting Intel SGX, maybe not so much, or a foreign government or something like that. So yeah, it's a hard problem.
Oh, and we have a mic now, so.
So I wanted to talk a little bit about the JTAG interfaces that are on everything, and specifically even situations like Actel's military ASICs that turn out to actually be not write-only. You can't actually read back out of the chip.
Yeah.
And so when you have those kind of underlying foundation technologies that are broken, either accidentally or intentionally, and those with Actel, but how do you deal with that? And I go back to kind of Ross Anderson's seminal paper about, programming Satan's computer, right? When you can't trust anything underneath you,
Yep.
how do you deal with that? And do you have any ideas on that?
Yeah, the best way, I mean, it's a horribly complicated problem. The best thing I can think of is the way the HSM solve it is to put everything inside a physical barrier and have very limited interfaces exposed to the outside world. So yeah, there might be JTAG inside, but the only interface you get out of it is a serial port or a USB port, and that's really the best thing you can do today. There's everything that's in the TCB you have to trust, and there's all sorts of risk of maybe there's a backdoor that gets, so physical attacks are less, you're not going to have a post-manufacture time modification inside your own hardware without a human doing it, but yeah, the stuff we have now is horrible. There's nothing, yeah. I have no idea.
Maybe you covered it earlier. How do you verify tamper-resistant HSMs to be cryptographically secure?
So the way people verify them in practice is they partner with the manufacturer, they get designs, they verify that the design matches the instance they have matches the design, and then they do, most of the verification I've seen has been on the software side, and a lot of the vulnerabilities, while doing hardware tamper resistance is really hard, doing reliable software is actually even harder, at least in practice. So Ross Anderson's group at Cambridge actually found some of the biggest bugs in HSMs that are public. The IBM, I think it was the 4758 back then, had bootloader problems and application problems with some banking related software they had running on it, so you could extract keys effectively. So yeah, doing the software verification is where the majority of effort that I've seen has gone, and just making sure the hardware matches up. There's been, the FIPS process largely is viewed as the standard, but the problem is HSMs, because they're so expensive, the main users for them are regulated industries or government that have a lot of other security measures built around them. If you're inside a SCIF, you're not really going to worry so much about somebody bringing in a huge amount of equipment to do hardware attacks on it. You're worried about software attacks. You're also worried about someone exfiltrating the physical device and then attacking it off-site. But they put a lot of effort into protecting the hardware and not letting people take CD-ROMs and stuff back and forth out of their SCIF to wherever. I'd say software verification is the number one area for this, and that's why having as limited functionality as possible is key for them.
And we have 10 minutes left for questions.
No, wait for 1 second.
Have you thought about other use cases like secure password hashing? I think I saw somebody at Google had put something in GitHub for password hashing, I think with UBHSM, even though it was a little bit flawed.
Yep.
Have you thought about those use cases? Do you have anything to say?
Yeah, HSMs are actually a great device for password management. There's a lot of problems with, the password management for consumer websites is should be a solved problem, but isn't. There's the school of thought that says you should put a high work factor expansion like hashogun like bcrypt or scrypt in there, but then you create the possibility for a DOS attack on your own servers. And there's a lot of applications where you actually do need the raw passwords, like if you're connecting to legacy third-party sites that don't do auth or whatever. So the idea of putting all passwords inside an HSM or encrypted under a key that's managed inside the HSM is a great idea, and it works really, really well with very low functionality, low, inexpensive HSMs, and would be a large use case. I think DNSSEC would be another wide use case. Just managing host credentials like SSL certificate stuff for SSL is a great use case. SSH keys potentially, but you probably don't care so much about your SSH keys because you can just rev them. If the machine's compromised, it doesn't do you so much good. There's a lot of cool stuff you can do. So I think definitely having something that people can experiment with and build applications for is going to be a feature. There's also end-user password management. So there's the whole thought of using these on servers, but there's also the side of using them on the client to be able to do things like offload all of your authentication credentials into effectively a smart card or an HSM or something, and that gives you a lot of benefit. You could put, if you're using them just to contain keys, there's always the problem if someone owns your hardware and asks it to log in for you, but you could potentially build something that puts details of a transaction in a trusted piece of hardware and shows you a keyboard, or a display in a keyboard to tell you. The YubiKey Neo actually has a physical presence button on the side, which works pretty well. I know Google uses those. So yeah, there's definitely a lot of potential for cool applications for it. And if they're $50, I think people are going to start doing that they don't do for $30,000 devices.
With your design, are you looking at any ways to support clustered servers?
So definitely key migration and being able to have different keys. So there's device encryption keys and key encryption keys that you'd be able to within the application. So you could have the same publicly accessible keys available on multiple devices, but just direct attached devices for servers. It would be, so when the devices are $30,000, you can definitely do something where you definitely want to do something with like a networked HSM where you've got a bunch of front ends talking to it, but I think these are low enough performance that you'd actually want multiple devices in most cases. For failover, you'd actually probably want to have the keys replicated rather than sharing calculations on it.
Cool. Going once. Going twice. All right, let's give Ryan a huge round of applause. Thank you.
Thank you. Using some of this technology, some other technology. We have some cool stuff to announce, but that's going to get announced later time. So the big question is, why do you care about this at all? It's because there's some threats that you face as a computing user. You face these as a sysadmin, you face these as an end user of the system. These are physical attacks on your hardware. If anyone gets access to your physical hardware, which normally your employees do, they can do all sorts of crazy attacks. They can image the contents of your disk. They can add hardware to it in the form of implants to do key logging, to do all sorts of other crazy stuff. They can tear it down. They can put it in a scanning, tunneling microscope. They can use a focused ion beam workstation. They can pull keys off of it, all sorts of crazy stuff. It's not so scary when it's a $5 million lab required to do this, but some people, Zach Brown and Adam Laurie, have actually gotten it down to like $10,000 or $20,000 worth of hardware to do some really aggressive attacks using like common off-the-shelf things from eBay. So it's kind of terrifying. There's all sorts of attacks, obviously, if you get system console access to a system. You can usually bypass most system access control mechanisms. Static crypto usually does protect you, but doesn't protect you from the evil maid attack. And my friend Eric Michaud and I have been working on some systems to detect evil maid attacks using nail polish, auto paint, and an iPhone as like applied to surfaces, which is kind of cool. Of course, if you get access to a system locally on the system, if you can do a root exploit, you can run all sorts of memory attacks. You can read out any location. You can do stuff. And there's also the blue pill attacks, hypervisor attacks, everything else. So it's pretty scary. And of course, in the cloud, you don't even see your hardware. You might never see your hardware. So you want a property called remote attestation where you can prove what's running on a remote server. And you don't even know if you're talking, if you're dealing with a virtualized environment remotely. So it's a pretty scary thing. But there's one really big threat that all of this stuff, insiders. We've seen organizations that have $50 billion a year budgets, cash, learned a lot about cryptography in the process, and also about living outside of the US and working on cool stuff. Then started an offshore data haven, HavenCo, back in 2000. It was a World War II anti-aircraft pirate radio platform that declared itself a sovereign country back in the 60s. We set up a bunch of data center stuff on it and did a bunch of hosting. It was like a really big thing for about like 2 or 3 months, and then sort of like a less big thing for another couple of years, and then sort of like there's a fire and some other stuff. Then I worked on RFID and NFC payments, so cool stuff where you use tamper-resistant smart cards and things to do NFC payments. If you go to a Jack in the Box, you'll see some stuff that I worked on. I actually went to Iraq and Afghanistan from 2004 to 2010. I worked on satellite networking, cellular systems, wireless communications. I bootstrapped a small defense contractor with like $2,000 and lived out in the wilds of the city and didn't get killed, so it was pretty fun. And now I have a trusted computing startup, CryptoSeal. Since 2011, we've been working on some cool stuff.
Oh, wait, no, that's not actually the talk you're going to be giving. No, I'm actually here running streaming, very much looking forward to this talk on building genuinely trusted computing that you can actually audit. So please, everybody give a huge round of applause for Ryan Lackey.
Okay. Good morning, everyone. So today we're going to cover why do you need to trust your hardware, some historical and current solutions in the space, design goals and some building blocks to build something better, an open design, and we're going to have a discussion about how this should proceed. Just as a brief intro who I am, I guess I got involved in cryptography as a cypherpunk back in the 1990s, like 92, 93, when I was like 12 or 13 years old. And I was really interested in eCash. And back then, you couldn't export crypto from the US, so I moved to this little island, Anguilla, to work on some open source, anonymous electronic with huge amounts of screening for employees and physical security, software security, best-in-class cryptography, everything else fall to a single insider. So if you think they have great mechanisms to protect and they still fall against it, if you look at your organization, you're going to have even more problems. So generally, people are worried about protecting a few kinds of things. At highest level, they're trying to protect keys. So they can do access control on those keys. They're worried about the general data you're processing, and they're worried about integrity and provenance of calculations. So you want to make sure that the keys you use in cryptography are protected, because these are usually long-lived keys. You can have keys, like I stupidly have a PGP key from 1999 still. So the compromise of a key during any of that period can be a major problem. Data confidentiality is usually protected less than the keys, but still it's a big problem if you've got, yeah. But this is a really, really hard problem to solve.